Module 6X, another example of sampled acquisition. There are some quantities that we see every day, and if you want to measure them, requires actually sampling. The example here is measuring rain. So rain is measured as a unit of length per unit of time, for example, millimeters per hour. So call x of t the rain intensity, and call y of t the cumulative rain from 0 to t, so that's the integral of x of r from 0 to t. Now, in the picture that you see here, which happens to be Lausanne, and actually the rainfall is straight onto the EPFL campus, you can see that rain can change rapidly over time and is very much dependent on location. So how do you measure rain? Well, you cannot have an instantaneous measurement of rain. What you would do is you need a surface. Over this surface you accumulate the rain, and then every now and then you look how much rain actually has accumulated. Now, the most common method that is used, for example, in sensor networks, in meteorological stations and so on, is a so-called tipping bucket. So in the picture on the left you see a sensor scope measurement station. That's a station that was developed with many people, but mainly at our laboratory, to do wireless sensor network measurements. And on the right side you see a tipping bucket. The tipping bucket has an opening on the top. That's the opening of the cylinder that gives a surface. And at the bottom we have a little bucket, and once the bucket is full, so if enough rain has filled the bucket, it will tip over to empty itself and generates an electrical signal. So the measurement we get, U of t, is actually a sequence of Diracs, and our measurement is the amount of rain that is in the bucket multiplied by the sum of these Diracs over time, which is when the bucket has actually tipped over. So the measured cumulative rain, V of t, is the integral of U of r measured over time. So let us look at this cumulative rain. So y of t was the integral of x of t. X of t was the rain that is falling. Y of t is the integral. And so it's a function that is monotonic and increasing. Sometimes it is flat when there is no rain, and then it increases when there is rain coming down. So what we are trying to measure is this cumulative rain. Now we have the cumulative rain, which is measured with this tipping bucket. So that means every 0.2 measurement units, the bucket will empty and you get an electric signal. So you see these gray lines horizontally, and every time the blue line crosses one of the gray lines, you have a Dirac that is generated or an electrical pulse. So you see the red electrical pulse every time the blue curve crosses over. Now, the cumulative rain intensity is the integral of these Diracs, and that's a red curve. So you see the red curve, which is what we really see as a measured cumulative rain, is actually not equal to the blue curve. It's only equal to the blue curve every time that the bucket tips over. And finally, we have the measurement error, which is the difference between the cumulative rain based on the tipping bucket and the actual cumulative rain. And so you see you have an error that is always bounded. So you're within 0.2 of the actual cumulative rain, but you're very rarely actually exactly measuring the cumulative rain. Okay, now this is very different from the sampling theorem of Shannon, as you can see. We have sampling, but the sampling is non-uniform in time. So every time you have a tipping bucket, you get an impulse, and you know at that point the exact measurement of the cumulative rain. In between, you're not sure what's happening. And so this is a very different way of doing signal acquisition and sampling. And you can see that it does approximate the blue curve, but there is an error. Fortunately, the error is always bounded. Okay, now this is exactly what you will see when you operate a meteor station and you're looking at the rain that is being measured by such a meteorological station.